Welcome to the Machines and Molecules podcast. Machines and Molecules hosts guests that have backgrounds in biotechnology, biochemistry, and machine learning. Our guest today is Marcus Bühler, the McAfee Professor of Engineering at MIT. And this is the first in-person recorded episode, actually, at MIT. Marcus is known for uncovering how nature builds extraordinary materials from the simplest molecular motifs. His work bridges atomistic simulation, multiscale mechanics, biomaterials, and the newest waves of AI-driven materials design. He's written foundational books, translated protein structures into music, and worked in simulation-based methods, cross-hierarchical methods, and lately in agents that drive self-directed materials research, basically automating the scientific process. Hi, Marcus. Really nice to have you on the show.
Thank you so much for having me.
So, how are you today?
Pretty good, yeah. It's early in the morning.
It is.
We have a busy schedule today, so yeah, thank you for making time and having this conversation with us.
Thank you for making time. Yes, we're sitting here at 7 in the morning because right after you have the next meeting. So maybe you can tell our audience a bit more about materials research by telling us what you, in your view, the most important universal principle of materials is that newcomers have to absorb when they enter the field of materials design.
Yeah, I think one of the most important features beyond sort of the obvious ones like hierarchies and things is probably adaptability. And the fact that biological systems have a built-in generative algorithm that allows them to do this. So they're not programmed necessarily to achieve a certain function forever, but they have this built-in ability to change and adapt and respond. So they're kind of computational algorithms in material form. And I think that perspective gives us a lot of insights and also opportunities as engineers to exploit these systems and direct them in ways we want to have them behave.
Does that mean, so the materials do not have to go through changes like genetic changes in order to change what the protein actually looks like, but rather the protein as it is, for example, let's say a protein, is already adaptable?
Yeah, I mean, it's both. I mean, there's obviously, so that's one of the themes of the work we've been doing is actually the fact that structure really is a snapshot in time, and then we have to understand structure and function evolving, right? So there are different time scales. There are obviously evolutionary time scales, which are much longer, and they adapt as well. But there are also functional time scales on the scale of maybe days, weeks, months in a human, or in organisms maybe even shorter, that have this adaptability. So a system like a protein by itself might not have adaptability to a large degree, but if you're looking at maybe spider silk or bone, skin, materials like these, they definitely have an ability to evolve on a pretty short time scale and have sort of these mechanisms built in that allow them to deal with never before seen circumstances, and how nature can adapt them very quickly is, I think, one of the stunning examples. So you go much faster than evolutionary timescales in that way.
Can you give an example for me, who's more versed in the pharma space of chemistry and chemical design for materials here?
I mean, you look, for example, at a spider web. You have the ability of the spider web to withstand significant mechanical loading in sort of scenarios that are not necessarily known by the spider in advance, as it lives in the actual environment. So it has to be able to deal with wind loading and mechanical loading, different kind of prey. Maybe another predator steals the prey out of the web. So there's a lot of mechanisms built in that give resilience, and it's not something that comes from a single property in one scale, but actually is an emergent behavior across different scales. Now, if you're looking at at the spider web, actually, as an example, the spider itself is the agent to construct the web, right? And so what I mean by the adaptability is that the spider can actually construct the web in different environmental conditions, right? In different geometric locations, different environments, wind loading. And that's what I mean. So the spider is the agent that's part of the system that builds this material. And bone is another example. It's a very obvious one. I think maybe more in the biomedical field. Bone can heal itself. It has the ability to overcome significant loading, different kind of fractures, and it is built into the process, of how this material establishes itself, as opposed to engineered materials, which oftentimes built to work, and when they fail, you have to go to the repair shop and kind of design them again or fix them up there.
Yeah, you have talked about different scales and about failures. Is there a failure mode when you design that becomes especially evident when you look across different levels of the hierarchy? Or how can I imagine gaining insights from jumping the hierarchies,
Right.
say for failure as an example?
Yeah, I think one of the failure modes of human analysis, no pun intended, actually, is we look at the world really in these hierarchies. We like to do that. We like to look at, molecular scale. We like to look at maybe the mesoscale, organisms, ecosystems. But the function of, let's say, resilience in a mechanical sense, or even in a different, ways to look at it, comes from mechanisms and effects that happen simultaneously at different scales.
Yeah.
Okay, and so there might be a certain defect, in fact, that forms at the molecular scale, which by itself, as a human looking at this, you might think, well, that makes no sense. Why am I adding a defect? However, when you look at the defect in the context of larger scale phenomena and effects, it makes sense. And suddenly, this defect actually plays a role in creating something much bigger than just a defect. It creates a network of energy dissipation mechanisms, which really link across scale. So one of the things we see is that, we look at sort of as humans into the world kind of like how we perceive it, which is, the macro level and down. Nature and biological materials and systems oftentimes have a much more holistic perspective on the different scales. And that's been part of the work we've been doing, is to figure out these algorithms. So what I talked about earlier is sort of what are these sort of new ways that I want people to think about, and these are the generative algorithms. So we think, well, what is sort of the compute that a material or an organism does to achieve a function? And I think if you understand it like this, you go away from this purely geometric structure-function relationship, but you look more at a dynamical process.
Yeah.
So the motion, the movement of how structure changes because of certain cues becomes the thing you want to focus on. And what you want to do as a scientist and engineer, you want to, of course, figure out what are these mechanisms, what are these algorithms, right? You're not happy just with looking at what happens in nature descriptively, but as a scientist, as an engineer in particular, you want to kind of figure out what are these elementary mechanisms.
Or be able to use them to your advantage, where the problem, of course, say in molecular dynamics, is you can't, like, what you would like to do is you would like to simulate at the smallest scale and see what happens in the largest hierarchical scale, but it's just impossible computationally.
Right.
Are there newer ways that go around this? I mean, I've exited like active MD research like 10 years ago or something. What are the new developments? Are there new developments there that you would say now cross these hierarchy levels better than, say, just going to larger timescales?
Right.
So, as we called it, coarse graining, for example.
Yes and no. I think for us, we have been doing and are still doing a lot of MD. But what we've learned, I mean, and I think everyone knows, is sort of the brute force MD is not necessarily going to get us to these principles. And that's really the biggest failure mode, I think, is that you can simulate 1 trillion atoms maybe one day, and maybe over maybe an hour potentially, right?
Yeah.
But even if you had this kind of computer which could do this, you wouldn't necessarily have the insight into the principles or these generative algorithms, right? So that's sort of the thing that we found very difficult. So now, within the limitations, so there are advances in potentials and force fields. I mean, we're in a position now where we can make a force field for almost any compound with machine learning potentials and other methods. There's some computational challenges a lot of times, but we've made a lot of progress there. I mean, compared to, let's say, 10, 20 years ago. But the overarching problem remains a little bit, how do you convert all these statistical trajectories into something that's meaningful?
Yeah.
And that is probably the thing that we've been focusing on a lot, is sort of, okay, we can run these simulations, but can we be smarter about which simulations we run? And of course, sort of that's what I've seen in my career. There are brute force labs that say, let's just simulate everything first principles, and that's okay. But there are other labs that have said, I'm going to run really clever simulations. I'm going to run really good experiments, so computational experiments. And that probably is the direction that I've been most interested in, because of course compute lifts you up, but you still have choices you want to make.
Yeah.
And you really want to kind of put a simulation trajectory in the context of what you're asking, right? So not just say, I'm going to simulate something and see what happens, but can I ask a question? Can I build a representation of the world that I haven't seen before? And that's really what it's about. So say, I believe, this mechanism is real. All right, let's build a simulation to test it. So what are the 3 simulations I want to build? How do I build them? And that sort of leads sort of a little bit to the later work we've been doing, is how do we automate this process?
Yeah.
Right? So it's not just about humans deciding, which is the slow process, but can a machine build its own representation of the world, whatever the world is, that be a particular chemistry, a particular molecule, particular material, and then using all these different tools as a way of getting data, essentially.
Yeah, definitely. I mean, we've basically worked on this for a long time with analysis tools like transfer operators, for example, were worked on in Berlin, which basically is taking MD trajectories and trying to gain insights from them. But it's rather, you have the trajectories, you gain insights rather than the other way around. I have an insight I want to test, and how do I make a trajectory exactly for that? Can you go a bit into, can you make a very concrete example of a manual, say, design? I want to test the following hypothesis with, say, a simulation. How do you set up the simulation? How was that thought process before you started automating?
Yeah, I mean, it's exactly. So that's a great question for those maybe new to the field, or maybe I want to understand a bit more about how this works. Yeah, I think, let's say you're interested in proteins, spider silk, or maybe something really cool like that, or maybe collagen or bone, right? And then you have a hypothesis that says, well, I believe, that the defects we talked about earlier are there for a reason, and they're not weakening the material, they're actually strengthening the material. And I believe this is because once you create little small defects and you put it into a network, maybe they become much more effective, and they actually create sort of the counter effect. They don't weaken the material, they provide a dissipation mechanism. So let's say you have this idea. You could set up 5, 10, 20, or 3, different scenarios, and actually build the system and say, I have 3 different designs of 10, 20 different designs, and I'm going to simulate what will happen. So the beauty of MD, of course, is that you create sort of a first principles representation of the world. You don't have a lot of approximations, and then of course you have potential, but you have time scale limitations and all that stuff. But you can say, I can sort of understand the trend, right? I'm not predicting exactly the strength, but I can see whether what I believe is true is actually true. Like if you create more defects, the material becomes actually better.
So creating defects in the very beginning before you start the simulation.
Exactly.
Yeah, okay.
Exactly, and that's a way I think we have been working on for a long time, because we can't necessarily evolve the material, the process itself. That is a challenge, I think. Sort of the question comes from that: can you simulate the actual process of creation of the material? That's very hard, so timescale limitations. Yeah, but in the most direct way, you would create it manually, create different protein, different structures. It has become easier since we have, let's say, protein folding tools and things. That's actually sort of on the AI side of things. It's been able to do a lot of things we couldn't do 10, 20 years ago, even 5 years ago, because we can make up hypothetical proteins and fold them and test them and get physics out of them. Yeah, so that's typically the process, and then you collect data.
Yeah.
And then, of course, you might go back to these trajectories that you mentioned and analyze, so I've seen the strengthening now. And the reason why we love MD, or at least our method, is because I can not only see the strengthening, let's say it happens, but I can actually understand why it happens. And so I can do these trajectory analyses, or I can look at the dynamics of, bond rupture and things. That is really, I think, the biggest value proposition of that method is that you start from a sort of a universal force field, and you simulate trajectories, do basically just the mechanics, and you analyze what's going on. And it's simple, and it has to be simple. I'm a big believer, if you construct really complex models, you have the danger always, you make them too specific, and you might actually put a lot of what you believe to be true into the model itself. So MD is awesome because you don't bias the predictions significantly if you do it well.
I mean, the other thing that I keep coming back to, especially in these times when people tend to do lab experiments and then go directly to machine learning predictions based on the data that was generated in the lab experiments, it's just much cheaper to do simulations as compared to lab experiments. It's very costly compared to statistical machine learning, but it's very cheap compared to lab experiments, actually.
Yeah, I mean, I'm a big fan. I mean, my philosophy, as you know, maybe some of the listeners will know, I mean, we're big believers in silico reasoning, you know, and that involves physics, first principle simulations, all those things, because it's cheaper. And actually, I think, you know, empirical evidence is important, but you want to really minimize that because it's by far the most expensive modality. And the other, I think, failure point behind a lot of these sort of recent, I think, developments is that you really have to specialize your hardware. Particularly, I think, you know, you're dealing with a certain chemistry, a certain process, and you're biasing your answer to that belief.
By using a certain way of doing an experiment and a measurement.
Exactly. So I believe, you know, if the more you can take the bias out of this reasoning process, that involves running MD, because if you believe in first principles potentials, or even, you know, DFT or similar flavors, you don't necessarily bias your choices. I mean, of course, we're in an ideal world, but you can be pretty agnostic to what you're looking for.
That's true.
And then you discover. Then you go to the lab at the end, you say, now I found it. But I think the search space is something that's important to keep very broad for discovery and for design.
With the downside, of course, of I'm doing an MD simulation, how do I draw inferences from the simulation that give me insights about kind of a real world phenomenon that I'm really trying to gain insight about? Like, how do I make the connection? How do I calibrate? That's kind of the downside that you have to live with when you do that.
Exactly. So I think there's, I mean, in the work we've done, we look at different scales of modeling and simulation. I mean, you can do big scales with MD and discover you know, features that sort of happen across scales. We look at invariance, we find, right? So is there, you know, no matter how you look at the problem, are there mechanisms, for example, that are shared? So these are shared abstractions. Like if you can simulate fracture, let's say, or a certain type of adhesion event, and you can see a similar mechanism, like we talked about defects earlier, size effects. If you can see this in an MD scale and in a coarse grain scale, you can connect the dots. The other mechanism we've been using a lot are, you know, more mathematical tools like category theory abstractions. So where you say, okay, I have a bunch of observations, and you know what I described right now with connecting, let's say, a coarse grain simulation with MD, or even an experimental observation, is sort of human intelligence working on this problem and saying, well, what are the shared ideas? And you collect evidence and you find them. And then you say, well, I found something that's an invariant across many different systems. So that seems to be a principle of nature that I can use. Again, in compositional, you combine something new. But the truth is, mathematically, we've been using category theory for a long time. So we started 15 years ago actually with this. And that sort of was our entry to AI, because we were modeling the discovery process and trying to say, well, if I don't want to have a human write a paper and read it and then make the connections, can a machine, or can an algorithm be developed that can do this? And category theory is the math of relationships. So that's been a big theme of my lab actually for 15 years. Very slow start and sort of explosive developments in the last couple of years, because machines became better in working with these abstractions and particularly neurosymbolic models that really drive this process.
Interesting. A friend of mine who is now in AI, he said he did something completely unrelated, namely category theory in his undergrad. Okay, interesting. So you've mentioned moving into AI. Maybe we can dig a bit deeper into that. So you said you entered through category theory, trying to find out how people make conclusions from the data they gain. So how have you started teaching machines to come up with general principles rather than just simulate things?
Yeah, so I mean, maybe we can go back to the question you raised earlier about the MD, right? Let's say you run all these trajectories if I give and I might have run thousands of simulations in my lab, and I'm giving a talk. Let's say I'm visiting your university or your company, and I'm giving a talk, and I'm not going to show you every single atom, right?
Yeah.
I'm going to show you schematics, pictures, maybe a graph that show relationships, and say, hey, this sequence pattern is really important because it controls the size of the nanocrystals in silk, and that in turn is important for the strength. But I also need amorphous regions, and by the way, I need the ability to form micelles because the silk needs to be stored, right? So it's really a story I'm telling you, and if you mathematically want to capture this, it's our story of relationships, right? So the context for where this sort of element sits, stability of a crystal for this particular property is important, right? It depends on what is it related to, and what are the ultimate outcomes, and so this process is something that we can model in category theory. So we can build sort of systematic representation of the world in this way. And then we could also look at related systems, and we can then say, oh, I have a crystal. This crystal is not only important for strength in silk, but actually crystals are important in engineering, and this is how they're used in engineering. So you're creating a web of relationships.
Yeah.
And in this web of relationships, so when we teach machines how to do this, we can make machines discover these relationships from data.
Yeah.
The machine can also and that's more recent work, not only discover this from data, from papers, but also generate its own data. We can have a relationship might be a hypothesis, okay, that is a result of a function that might be a simulation. So you can say, in order for me I hypothesize that the strength of the material is related to the crystal, but it's either a fact or it could be a question. So in a category theory framework, you can describe relationships in many different ways, including as facts or questions or functions, actually. So this itself could be a function, and it could be an MD simulation, or it could be a hypothesis generator that would test the stability or the validity of this statement.
How do you automatically identify entities between which relationships can be formed? Because I'm not very much into neurosymbolic models.
Yeah.
How does that work?
Well, you have to think about, if you use a neural network, let's say use a language model or maybe some other representation, you describe language in a really gigantic, embedding space, and you're extracting some symbols, but the symbols are very, very wide and broad. There could be language, there's a lot of edges to this, and the edges are kind of smoothed out. That's the point of language models, I think, or neural networks. They're very good in providing a glue between ideas.
Yeah.
What we're doing in finding these representations is we're forcing the model to make a choice and say, okay, instead of having an infinite number of, representations, or very close to infinite number of representations, can you find these very this reduced space of symbols, okay, or relationships, and both of them are in there, like a structure, a crystal, or a relationship like effects or influences or hypothesis. And you force the model to understand the world in this more abstract way.
So you're doing quantization, an alphabet of entities that it's allowed to use?
Exactly, yeah.
Okay.
Yeah. And I think one of the things you can either force it rigorously and say, I'm going to only use like 3 or 4 different entities, or you can let the model discover on its own, a sort of minimalistic way, but it can expand the vocabulary or the range of descriptions as it needs. And that's actually the reason why this works well with modern sort of AI tools like language models, because in the past, if you were to take very traditional methods of maybe knowledge extraction, you would oftentimes create very brittle representations because you have these discrete choices only.
Yeah.
Something like a language model has sort of very powerful capabilities in that it can do that, but it can also tell us, okay, here's an edge case, I need a glue, which is not yet understood as an abstraction, but it's necessary actually to provide a connection between something like silk and bone and maybe a social network. And so this allows us some ability for the system to actually work from an engineering perspective.
But how are language models less brittle? Are they just less brittle because still we have a fixed vocabulary of tokens that will be used and reused, and suddenly the difference of language models nowadays is that they absorb so much knowledge into the statistics between the tokens rather than the tokens themselves. The tokens themselves are still fixed, right?
Yeah, I mean, the language models generally are able to, if you just think about this sort of how do you create symbolic abstractions,
Yeah.
they're able to, understand very discrete sort of level symbolic
Yeah.
representations, but they also understand, let's say if you talk to them, human or natural language, right? So they can actually sort of explain an abstraction, but also the relationship in natural language. And that's a glue, or we see it as a glue. So if you're deviating from, let's say, a purely symbolic representation, you have a language that's, in the same embedding space. So the model understands both symbols and less constrained representations.
Yeah, yeah.
And that's really the power of it, yeah. Of course, you can also work entirely in, let's say, embedding space, and that's some work we've done as well, where the model doesn't actually talk to us in natural language, it doesn't decode, but actually does a lot of thinking purely in the internal embedding representations. And there, you lose maybe some of those edges you want, because you want the model to make a choice. And the question really becomes more from a more philosophical, or let's say from an algorithmic perspective, where can you generalize the most? So can you find these universal operators that describe vast sets of realities and phenomena, and where do you need specialization? So we call it sort of finding the differences. So we say always science is sort of this, the art of differentiation, where you understand, okay, I have shared principles, but it's also okay to have differences as long as I understand them. So we train the models to be penalized if they have differences that they cannot explain, right? Yeah. So the way we're training them is you should find universal operators to describe your phenomena, and that could be symbolic representations. But it's also okay if you can organize differences. Like an example in a PDE would be, you have a phenomena, ABC, like fluid mechanics, solid mechanics, and whatnot. And these are all the solutions, basically the same problem, the same PDE, Newton's laws, ultimately. But they applied with different boundary conditions, different contexts. So this is a perfect illustration of understanding sort of universality, which is the differential operator, Newton's laws, but also differences, which is the different initial boundary conditions and so on. Now, the problem would be we penalize the model if it doesn't capture these. So if this sort of has unorganized territory, if you wish, that where the model sees the phenomena that it cannot explain, and it has to provide sort of single-shot answers and say, I can't explain it, I could just memorize it. So this is what we penalize the model. Yeah, yeah. So this is how we train the models to do this. And there's different ways to do this. Like we said, I'm using language as a method. You can use embedding spaces as methods. But you have to find a way to, give the model some incentive not to cheat. In other words, memorize. That's the biggest failure mode, I think, of machine learning today, is that the bigger you make models, the more they can memorize.
Yeah, because they can memorize randomness.
Exactly. And so what we've spent a lot of time on actually is exactly figuring out how do we avoid models from memorizing, but actually finding these deeper abstractions in the world.
Can you maybe talk a bit more about how you use AI, not how you train AI models to find these relationships and entities, but how you use AI models then to make scientific discoveries in an autonomous mode? Like, how do you glue together the different building blocks so that you maybe in the end, I'm not sure how your system works at the moment. Do you give it a question and then let it run, or do you or how does it work, and how does it then do its magic?
Right. Yeah. So there's different things models can do. You can ask them to do. Okay. So I'll walk maybe through a couple of different methods and things, but. The first thing we have to realize is that the models, the way we know them today, most of the time, will not work for this type of task. Yeah. Like if you imagine taking a trained model, and it would, you can't ask this model, give me this answer to a new discovery, and that's it, right? So models have to be able to do discoveries, they have to be able to learn on the fly. Yeah. And it seems maybe obvious once you think about it, but it's not the paradigm many, in the field are using right now. Right?
In the sense of, you can't just use a pure language model without anything else and ask it the scientific question and expect it to give you a proper answer.
Exactly. And the reason is sort of, very basic, is that you train the models to predict the world as it is. Yeah. Versus in science, we want to discover the world than it is, but we haven't understood it yet. We haven't organized it that in that way. Or as engineers, we're building things that haven't really been built yet or have never seen them. So either one of those, whether you're discovering principles in science or whether you're explaining things that haven't been sort of connected yet, or whether you're an engineer and trying to build some new material or device that's never been made before, the things you're dealing with did not exist in the world. So if you train a model to predict what's in the world right now, which is what a language model is, or what any other, actually, even a machine learning potential is basically that, you might face issues, right? So you have to have systems that can go to the edges of what they know, and they have to build some understanding of when they fail to know things. Okay, so that's one of the basic things. So not only do they have to be able to adapt, but they also have to understand when they need to adapt, because you need to be, and that's a hard thing to do. So they have to learn to ask themselves questions so that they can give some assessment about their own understanding and realize, okay, I'm at the end of my understanding. And the way we're doing this is, so I talked earlier actually about sort of the objective function or the loss function we're using, and that is that we want to organize the world in principles and in differences, explaining differences. So if we fail to do that, we have a problem, basically. So in the way we're doing this practically is you say, oh, I have maybe you're asking a design question. That's an easy one. It's hard, but it's an easy one. So there's one of the type of questions we can ask. You know, make me a protein with these properties, okay? And it ideally would be, you know, properties not by itself alone. One, I mean, that matters. It's usually a structure, but also it has to be, you know, non-toxic. Maybe it has to be stable. You know, things like this. So even a simple question like design me a protein, there are many models that can do this, but they answer only one dimension of it. Let's say, what is the hypothetical structure? Well, maybe you can never make it. You know, maybe it's not actually stable. Maybe it's hallucinated. So a system needs to be able to understand all these dimensions. So in this case, the model will go and assess itself. You know, make a design. It's a prediction, and it has to have an ability to test this. Right. So.
And it does this through tools, then basically computational tools that it uses.
And the thing that we've realized in the last few years is that we can give it all the tools we have ever created. That's sort of how we started back in 2003. 2023. The years are sort of going by very quickly, but 23 was the first time we gave it basically a molecular simulation tool, a DFT tool, and we trained this system, this model, to not answer based on its memory, but actually to create a process to get to new data, to produce new data from a DFT, and then give us the answer. So fundamentally different, right? But then also, since then, you know, of course, and integrated in this is partly what we call program writing. So models are able to and have to be able to also make their own tools. And that's also possible now. So you have existing tools, and the tools might be provided by you. You might say, I'm scientist A, you know, or engineer B, you know, I have all these tools in my lab, my company, or I've used them. But, you know, the AI model goes on the world and will seek out tools on GitHub and, you know, API providers and things. So that's how we do it. But also can write its own tools. And that's sort of the remarkable thing. If you figure out, okay, I've used these tools, I've gotten sort of maybe conflicting evidence, right? So that's what the model will look for. We'll try to build a model of the world that makes sense in a way that, okay, I can explain this protein that I've made now. It's stable, it's real. There's maybe evidence in literature for this already. Okay, it solves the problem, right? But if the things are conflicting, the model understands something is wrong. I don't fully understand it, so it goes out further.
It has to dig further.
And one of the things we can do also is write programs. And that means either code or it could write a plan to execute and doing certain things. Might even ask you as a human to do things, right? Or a robot, right? So that's how the intersection of the physical world comes in. It's very important. But, you know, it will collect new data and it will explore. And it will basically be done whenever it solves the problem. Now, in discovery, it's a similar thing, except that we really focus on the principles. We say, you know, I want to understand maybe the question would not so much be design. It would be, you know, figure out why am I observing this transition from order to disorder in this particular class of proteins. And so now this model will figure out an algorithm that will explain this. And it could be, okay, here are different ingredients. It could be that the sequence matters, the process matters, the temperature matters, and it will explore all these different phenomena, and it will always try to dig holes because it has an awareness of its own prediction. That's a really key thing. Right? It's sort of a conventional AI model has no awareness. Actually, neither does a PDE. PDE doesn't know about its own predictions, it just makes predictions, right? So what we're really building is intelligence that has an awareness of its own prediction, limitation, generality. And so we have to build sort of that is programmatically what we have to train for. Not so much the answer. So that's one of the big sort of, I think, failure modes. People think, well, I'm going to train this model with more data. I think it's actually nonsensical. And I think we'll look back to this in the future and say, this is era of big data. I'm like, great. We need some data to understand basic things about the world, but discovery and engineering cannot be done with existing data. By definition, it would be, otherwise you would know it already, right?
Yeah, right. So maybe for the audience that's not too deep in AI, maybe the good, it's not even a metaphor. The good thing to think about is when you ask ChatGPT to do something for you and it doesn't it didn't catch what you really wanted it to do, and you give it feedback manually by typing in, no, I rather want you to do, I don't know, be shorter because this person has a stuffed schedule. So please change your text.
Right.
Now, what happens is not humans give feedback to the language model in this case, but you run a simulation, you draw some conclusions from it. These conclusions are fed back to the language model, and the model then says, okay, but this is actually in contradiction to this and that, so I have to dig further.
Right.
And then it hallucinates, basically, which is basically hypothesis building.
Exactly, right.
And digs into this hypothesis to find out whether it's true.
Yeah, exactly. And you have to make the hypothesis construction compositionally well done. And that's where we talk about compositional reasoning, which is a term for category theory, which means that you don't just randomly create a hypothesis, but you construct it. You say, because I know A and B to be true, and I know A and B to be related in this way, I also know about C, and I know that if I connect A, B, and C in this way, I can conjecture what D might look like, right? That's the way the models think, exactly. And so then you create these, like we talked about earlier, what we did back in the day, like creating these 5 or 10, 20 different simulations, right? This kind of work, we have to teach machines how to do that. So the burden of training, and this may be one of the big takeaways from the work we've done, is it shifts away, not so much training the model on things you know. That's the baseline intelligence. You still need to work on this, but there's something there. But it's really about teaching the models how to understand its own limitations and how to create strategies to address them.
To get new data to understand the world better.
And we train them by giving them reinforcement feedback. So if they do a good job, meaning if they create the right questions and they execute the program to test them, and if the insights are better, in other words, there's a better principal model and better understanding of the differences, we give them a cookie. They say, hey, you've done a good job. And if they have sort of done a poor job, in creating a question that hasn't furthered the understanding, we don't give them a reward, right? We give them a penalty. So we teach them really through reinforcement learning, I think, is a theme. There's a lot of details of matter and implementation questions and stuff, but generally, I think this is how we're moving, where we're moving. And there's a lot of questions and mechanistically, how you do it, what are the right frameworks, what's the right training algorithm and so on. But generally, that's where I see the world is moving to right now.
Yeah. Super interesting, and the time has run super fast. So the theme of the podcast is that our guests always bring a third M word apart from machines and molecules. Have you brought a third M word?
I did, yeah. Mine is material music, and you mentioned earlier in the introduction. I work in science, material science, biology, and all these different areas, but I've also worked in music. And one of the things I've worked on quite a bit actually is this connection between music and materials, and actually really coming from sort of what's the sort of the language of life, or language of matter in a much more abstract sense. So what are the commonalities between, let's say, something like music, sound, and the material world? And actually a lot of connections. The most obvious one probably is the fact that matter is moving all the time. We talked about earlier, so that matter isn't just static, it adapts. And vibrations are obviously a very important concept. Things repeat itself, and that connection between just the sort of cyclic repetition of the world and how things move, atoms, molecules, the vibrations they create in this process, and sound is obviously a very direct connection. So that's what your music sort of talks about, is this quantitative theory behind materials and music and the relationship between it.
And would you say that music can also be a different mode of perceiving things in material science? I know you've worked a bit on solidification. Is it that to you it's a mode of discovery as well sometimes, or has been in the past?
Yeah, there's a reason why we're interested in this, and that's that you look for really hard problems, things that aren't really connected, right? That's generally what science is about. You want to find kind of the most maybe contradicting observations and try to find unifying theory. So music or sound, human created sound, music and materials created through evolution, let's say, biological billions of years and adaptation. I think it was some of those phenomena where very few connections exist. I mean, there's sort of the obvious ones on the surface, but what are the latent connections that are more deeper, right? Yeah. That's been something I'm very fascinated with, because I think if we understand that, we can build a better unifying theory of the world. There are actually, I think, lessons learned, for engineering principles. I mean, there might be solutions that if you're looking back at sort of human intelligence, it's something that we can create in the musical space that are much easier to do there than if you were to build materials using, I don't know, like actual materials or math. There's different parts of our brain that work differently. And also that has informed a lot of the work at AI. We're thinking, I don't want to be too obvious in how I create my AI systems. I wanted to kind of explore on its own and find maybe mappings, right? So it's all about mapping things. Like I say always, it's like in math, we transform to Fourier space and other representations like this. Things become a lot easier there for some problems, right? And similarly, we think, if you map into musical space, our brain has abilities to construct high complexity with variation and creativity that has not been tapped in engineering yet or science yet. So that's one of the reasons. And we've done this. I mean, for that, we've also tried to figure out things fascinated with this. How do you open up new channels of communication? I mean, it might be literally like between an animal and a human, but or maybe some things that are not as obvious, like a spider's web and its vibrations, and humans. Can they talk to each other? Can we go to a concert and hear spider's web's vibrations and use as an instrument? Can we listen to molecules? Can a composer actually constrain him or herself by molecular scalings, right? So instead of having tuning systems based on strings and air at the macro level, which follows basically Newton's laws, and can it be governed by quantum mechanics, which is really what we see in a molecular vibration. And so now that tuning system is going to be very foreign to us, but what does it teach us, if we work with it? So those are some of the things I've worked in. I work in composition myself, so I've done a lot of music composition, and I've sort of used this very effectively to say, I want to get a really new substrate for me to write music. It's not based on sort of things we've done for thousands of years, but let me take an idea that's very new, like quantum mechanics, or these sort of weird vibrational spectra, and can I write music with this? Can it make sense for humans? What does it teach us? And there's a lot of surprises that come about in our thought process. So art is really, like science, it changes your understanding of the world as you go through the process of creating it and understanding it.
Great. Thank you, Marcus. That was a very fast ride through a lot of topics. It was super fascinating. Thank you for hosting the podcast here at MLT. And looking forward to catching up in the future.
Thank you so much, Ingmar.